Hello again. Today, inshallah, we will continue our lecture. We are going to expansions as I explained earlier in the morning. This is the third part of our lecture. We will talk about Taylor's formula or Taylor's polynomial or the expansion using Taylor or Maclaurin. By the idea, Maclaurin is just a special case from Taylor, as you would say. This is, we will try to deal with today the single valued functions in order to memorize what's Taylor and what's doing, and to go from Rn into R functions in several variables. I don't think we will be able today to take the expansion for vector valued functions. We are not going to have it, but this is generally how to use Taylor in various types of functions. Let's talk first about the case of Taylor once you are dealing with one variable. The law is really very simple. This is Taylor's polynomial, and it's easy to be memorized. All I have to do through Taylor is I'm trying to expand my function, let's say for f of x, to be to equal to in the neighborhood of a certain point. Let's say at x equal to a. All I have to do is to get the value of x at a plus the first derivative of x but at the point a times x minus a, then getting f double dash of x at this point, which is a, times x minus a to the power of 2 divided by factorial 2. Then repeat more than that for the various terms. So this is for a linear relationship or a linear polynomial. This is for quadratic. And for cubic, I will need to add this term f treble at a times x minus a to the power of 3 divided by factorial 3, and so on till you reach the nth derivative. So this is actually the nth derivative of f at a times x minus a to the power of n divided by factorial n plus the remainder term. And the remainder term, which makes the difference or try to make the difference between the function and the polynomial in approximation. So this is mainly how to approximate a function using the polynomial of Taylor. Rn is really very simple. It is the limit of x tends to 0 for the value of r of n of x divided by the magnitude of x and y, and it should grow to 0 for the error. And this is, I believe we did go through this previously when we were in the differential. So that's the error term, as you can see. So once more, the law of the polynomial of Taylor expansion, it's really very simple, as you can see. This is Taylor polynomial of order n at point A, and that's the error or the remainder term. As I told you, the remainder term is exactly that, the term that we was using in, if you remember, differentiability. So it's really very simple. Limit x tends to a of Rn of x divided by x minus a to the power of n, and is equal to 0. Once it's equal to 0, I can approximate f, or they are going to be the same exact values or very close to each other. Okay, functions with one variable. This is the law, as you can see. Also, I want you to remember that f dash a times x minus a, this is called the differential of the function of first degree. That's the second degree differential, and that's the nth degree differential. And the differential, it is the derivative of the function at the indicated point times x minus a. The differential, or the second order, or the second part, is going to be differentiating the function twice times x minus a to the power of 2. That's it. That's the differential, and it will be divided on root 2, as you can see. Also, the remainder term, it's exactly the same. either to use the previous equation or that equation, they are both of them correct. Once you make your expansion around A and B is equal to 0, we are talking about Maclaurin. So the difference between Taylor and the Maclaurin, it is the neighborhood of the point that you are using. If the neighborhood is 0, then you are using Maclaurin expansion. If it is any other point, then you are doing Taylor, as you can see. This is once more, as I told you, another identification of what's happening, or more clarification. If you look to the function f, which is on the blue, as you can see, this is the graph of our function. If remark at point A, the point of expansion, this is how to approximate using a linear relationship. So it's a Taylor polynomial of first degree. Okay, that's the difference between the values. That's the case if you are using a cubic function. That's the case of, that's the case if you are using quadratic function, and that's the case if you are using cubic function. Cubic polynomial. So this is actually up to the term. So if I am approximating f of x using just only f of a plus f dash a times x minus a, this is going to be the linear relationship, because it's going to be of first degree. For this function, it will be if you are approximating to the second term, so it's going to be f dash a times x minus a to the power of 2 over factorial 2 plus f, this is the double dash, just a second please. This is f dash over 2, okay, this is f dash, then plus f double dash at a in x minus a to the power of 2 divided by factorial 2. This is for the quadratic function. If I'm using the cubic, then I will add plus f treble x minus a to the power of 3 divided by 3 and so on. And that's actually the main reason that we are using the polynomials. It's easier to use, and it gives a very good approximation. So these expansions are used to approximate the value of the function at certain input value by various types of polynomials, as you can see, linear or quadratic or cubic or fourth order or whatever. This is why we usually find the expansion at certain point in the neighborhood of a particular point. This is once more the Taylor's law. So as I told you, if we stop right here, so it's going to be the case of the linear function. If I added this term, it's going to be the quadratic. If I added this term, then it's going to be the cubic function, and so on, as I told you. This is a very nice problem. He wants you to write Taylor's formula of order 4 at a equal to 0, which means Maclaurin expansion, for the function f of x e to the power of x, and he wants you to approximate, to use this polynomial, to approximate the value at 0.1. For all of you who are working with their cell phones, leave your cell phones. Leave them. The first step that I will do is to write the Taylor expansion formula. The second step, I will need to find the derivative of my function. So e to the power of x, the derivative will be e to the power of x. Second derivative, third derivative, nth derivative, all of them is just only e to the power of x. Now all I have to do is to substitute in this equation by e to the power of x, but remember that we are expanding around a is equal to 0. So all we had to do is just making a simple substitution. This is gonna be, just a second, this is gonna be e to the power of 0. This is gonna be e to the power of 0, which is 1, and so on for all of them. So the f double dash will be e to the power of 0. F triple e to the power of 0, blah blah blah. All of this e to the power of 0 till you reach e to the power of n. So all of them is going to be equal to 1. Then I will have x, then x squared, then x cubed, then x power 4, which is simply gonna be on this form. 1 plus x squared over 2 plus x cubed over 6 plus x to the power of 4 over 24, as you can see. Now I've expanded this function by this polynomial, which is a fourth degree polynomial. If you want to approximate the value at 0.1, all I have to do is to replace every x in this equation by the value 0.1. This is what we are going to do. So all we had to do is to just replace, as I told you, by 0.1. These are the values. That's the value of the approximation, and that's the exact value. As you can see, 1051708. This is just 0.9, as you can see. So it's really very close. The difference is related to the error term that exists in this expansion. In a similar manner, this is the shapes that we already did. This is the function which is e to the power of x, as you can see, and that's with the neighborhood of x is equal to 0. This is the linear function, that's the quadratic, that's the cubic, as you can see, and the fourth order function on the same graph. This is to show you how the values of these polynomials are really very close once x is equal to 0. And as long as you are in the neighborhood of 0.0, see, the values are really very close. As long as you go away from the origin, then the error will start to increase, and you will need to update your expansion around in the neighborhood of another point, and so on. This is also really very nice problem. He wants you to find Taylor expansion of e of x around x equal to 2 up to the nth term. So I will start by finding the derivative, then substituting in the main equation. Now, as you can see, this is f of x, e to the power of x, f dash, f double dash, f triple, up to fn. I will replace each value of x by 2. So now I have f at 2, f dash at 2, f double, f triple, fn. The next step is to start substituting, direct substitution. So this guy is e to the power of 2, all of them. And this is going to be x minus 2 to the power of 2, x minus 2 to the power of 3, and so on. That's the expansion that actually approximates this function in the neighborhood of 0.2. Similar manner for plenty of functions, if you need to find Maclaurin expansion, that's the power of having a good approximation. I can use it in programming, I can use it in scaling functions, in dealing with data, okay? So it has enormous applications, especially if you are writing a code or something. You can use Taylor or Maclaurin expansions in order to simplify stuff. معايا عمر? So of course, same way like this is f of x. So I will need f dash x, which is gonna be 3e to the power of 3x. So the key issue is to know how to differentiate. As you can see, that's the second derivative, the third derivative, that's the nth derivative. Start putting x equal to 0. All the exponential functions will be 1. Then start writing your law, then start substituting. That's the expansion of your function in the neighborhood of x equal to 0. As I told you, that's Maclaurin expansion. Similar manner for ln 1 plus x, and as I told you, you need to perfect how to do derivatives. So for this function, for example, f dash of x, it's gonna be 1 over x plus 1, which means x plus 1 to the power of -1 حسين. So if I want to get f double dash of x, the power will go down, then I will subtract 1 from the power, so it's going to be -2, x plus 1. If I need an extra derivative, x treble, it's going to be -2 times -1, which is 2. Then I will subtract 1 from the power, so it's going to be x plus 1 to the power of -3, and so on. So this is really very, very important to deal with, or how to deal with these functions. functions, as you can see. Okay? So once more, I already made the derivatives. Then I will start substituting instead of x by zeros, getting the values, then start substituting. This is really very simple. All of this is considered as a revision since you already know about Taylor and the Maclaurin expansion in one dimension. It's really very simple, direct substitutions. These are some of the very famous substitutions of functions: sin x, e power x, sin x, e to the power of negative x, and so on. And as I told you, they are used in plenty of applications. Okay. This is also just an introduction before we go to Taylor expansion, Mr. Omar, in several variables. I want you to remember some of the famous information. First of them, that the differential of f at AB is equal to f at A plus dx and b plus dy, where dx is x minus x naught or x minus a, dy is y minus b minus the value of the function at a and b. We did go through this in, I believe, in the previous two lectures, okay? So once more, this is how to find the differential. I will differentiate the function with respect to its variables. So partial f partial x, partial f partial y. Then I will multiply by dx and multiply by dy, where dx is x minus a and the dy is y minus b. Then this is the quadratic form that we are using. This is xy times partial 2f partial x squared, partial 2f partial x partial y, partial 2f partial y partial x, partial 2f partial y squared times x and y. That's the matrix notation. That's the quadratic form. We will need it down the road in the Hessian as we had previously in higher order derivatives. That's the first order derivative. If I want to find the second order derivative, differentiating this equation with respect to x or finding the differential of this function, will leave you with the result that you can see. It's a straightforward application of the differential of your first order function, and so the derivatives will be to degree number 2 or to the second derivative. Mr. Omar, you are stealing. So it's going to be partial 2f partial x squared times dx to the power of 2. This is going to be dx dy times partial 2f partial x partial y. Once more, Hussein, dx, it's x minus a, it's difference in x direction. dy is difference in y direction, so it's going to be y minus b. Okay, I believe this is written in a much better format. So this is the differential, okay, for the first order. That's the differential in second order. And generalizing this issue, this is the first, that's the second, that's the third order. I need you to memorize them. That's for the first, that's for the second derivative, and that's for the third derivative. Hussein, remark the coefficients. This is the third derivative of f with respect to x. That's the third derivative for f, twice for x, and the third was y. That's the third derivative of f, once for x and twice for y. And that's the third derivative of f with respect to y. Mr. Ahmed, one of the tempting problems in the exam is to find, for example, partial 4, partial 3x, partial y, or partial 4, partial x, partial y cube. So you need to be trained on this. And this was our topic 3 lectures ago. So you need to review these parts. Okay? Of course, Mr. Hussein, I've explained this part, or want you to remember this part, because once we start writing Taylor in several variables, this is going to be the case. I will have the value of the function at certain point. Of course, a here can be x and y, or x, y, and z, or x, y, z, and t. Do you understand what I'm saying? So it's an indication of a point in n dimension. Times, I want you to remember, this is f dash a times x minus a, which is the differential. this equation.
Yes.
Okay? And that's f double dash times x minus a to the power of 2, which all of it together, it is the second differential. Are you with me, Mr. Ahmed? And for the third part, remark this is the third differential. يا أحمد. Boss, that's the third differential formula. فاهم? This is how to apply it. If you don't remember those parts, you're not going to be able to deal with it in x and y and so on. So once more, Mr. Omar, this is the case using the differential, as you can see. It's exactly the same in one dimension, but in two dimension, instead of dealing with just only the derivative of the function once, twice, or third, I will deal with the differential instead. Okay? So functions with two variables. Remark that a function of Cn, that's the set of the determinants at A and B. This is tailored using the differential notation as I told you. And those are the relations in expansion. بص كده أحمد. This is the value of the function of A and B. That's the first differential. That's the second differential, or the second order differential. And that's the third order differential. Of course, what's making it so long is the substitution of x minus a to the power of 2 times y minus b and so on. This is exactly like this one, ya Hussein. They are exactly the same. But in the longer version, I've made the substitution instead of this part. Okay? This is substitution as I told you. That's an example of how to expand your problem. Don't you leave everything? Just look at this problem. Then I will leave you after it. Okay? So once more, you have f of xy, which is y to the power of 2 plus e to the power of x. This is our function, which is a function in how many variables?
2.
2. So I will need the differential for. Okay. Taylor's formula, order, blah, 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 blah. But please evaluate it in the neighborhood of the point
0, 1.
0 and 1. So I will need to find the following. Please focus. I will need to find the value of the function at 0 and 1. Then I will need to find the differential of the function at 0 and 1. Then I will need to find the second differential of the function at 0 and 1. Then I will need the third derivative or the third differential of f at 0 and 1 if I am expanding till the third term.
Okay.
Then I will make the substitution, and if you need to approximate something in the neighborhood of this point, you will be able to. Of course, in this one, you remember, this is going to be, in this part, Omar, it's going to be partial f, partial x in x minus 0 plus partial f, partial y in y minus 1. This is the first differential. The second, it's going to be bigger according to our equation. Okay, if you want me to write it with you, I can see it in your eyes, Mr. Hussein, it's going to be partial 2f partial x squared times x minus 0 to the power of 2 plus 2 partial 2f partial x partial y in x minus 0 times y minus 1 plus partial 2f partial y squared in y minus 1 to the power of 2. It's really very simple. But if you didn't write it using your hand, it's not going to be that easy. You will feel it is complicated and it needs a lot of steps, but believe me, it's really very simple. All you have to do is to resolve this problem as you can see.
Okay.
I usually do this. So the first step, as I told you, this is f at 0 and 1. That's the first derivative. Hussein, remark I'm multiplying in x, because it's x minus 0, so it's an x. This is going to be y minus 1. This is the second derivative. Same remark. This is x minus 0 to the power of 2. This is x minus 0. This is why I'm writing the x. And blah, blah, blah. Plus the remainder term. So all I have to do now is just a direct substitution. Partial f, partial x, partial f, partial y. I will substitute in 0 and 1 in both of them in order to get my value. For the second order derivative, I will need to prepare partial 2f, partial 2f, partial 2f for x squared, for y squared, for x and y, making the substitution. This is 1, 0, and 2. Then I will take these values and substitute in the expansion and just simplifying the stuff, adding the similar stuff all together, Mr. Muhammad, and simplify it as much as possible. This is gonna be the final value. So if I want, for example, to approximate near the point, okay, 0.1 and 0.9, all I have to do is to replace x by 0.1 and replace y by 0.9, as you can see. Then you will be able to get the value of your problem. I'm sorry, you will need to, in order to get these values, I will use x by 0.1 and y, which is gonna be near to 0.1, 0.9. Look to this point and the exponential point, which is 0 and 1. So the difference in y will be 1 minus, as I told you, will be 0.9, I'm sorry, minus 1. So it's gonna come up to minus 0.1. It's direct substitution in the main equation. So once more, that's the equation. This is 2, this is gonna be 0.1, this is gonna be 2 times negative 0.1, and so on. You will have your approximated value. That's also another problem which is exactly similar to what we did go through, but just adding the part of the gradient, because those numbers you don't need to evaluate. So this is really very good example to a problem in your exam. You're not going to be able, you are not going to go through the details of the evaluation of the derivatives. Mr. Muhammad, those are given in order to give you the values. So for the function at x and y, of xy in the neighborhood of 1 and 0, it's going to be f at 1 and 0. F at 1 and 0 is 0. I've given it to you. Then you will need partial f, partial x and 1 and 0. This is why I'm giving you the gradient. Because in the gradient, Omar is smiling, it seems he's sleeping. Okay, in the gradient for this one, it's going to be partial f, partial x at the point which is 1 and 0. This is going to be partial f, partial y at 1 and 0. This value is partial to f, partial x squared. That value is partial to f, partial y squared, of course at 1 and 0. That value is partial to f, partial x, partial y at 1 and 0. This is why all the values are given. So actually, although it is given and it's confusing, but it simplifies your life a lot. Okay. So all I had to do is to make the substitution, as you can see, and then it will be easy to evaluate directly by making the substitution. Just remarking, as I told you, that's going to be x minus 1, but y minus 0, which is going to be y. That's the final expansion. Then I can use the substitution of x equal to 0.9 and y equal to 0.1. That's once more the formula, and tomorrow, inshallah, I will try to solve with you some problems on the 3 topics of today. Thank you very much for attending. Please try to study today in order to make your life easier tomorrow, inshallah. Thank you very much. See you tomorrow, inshallah. Bye-bye.